All right, let's talk about single slit diffraction. So if you have one little slit and the light comes in and then you get this pattern like this, and we call that single slit diffraction. Um, Basically, the idea is everything's the same as what we talked about for double slit diffractions in terms of the equations, and the difference is our d sine theta equals m lambda. Capital D here, instead of being the separation between the slits, it's the size of the opening. And the other thing is that m here refers to destructive interference when m is an integer, 1, 2, or 3, and so on, or -1, -2, -3. So this is a little bit tricky because d sine theta equals m lambda will give you constructive interference for a double slit or diffraction grating, but for a single slit, d sine theta equals m lambda gives you the destructive interference. So m plus a half lambda will give you the constructive points in the signal. So there's 0, there's lambda over d, 2 lambda over d, 3 lambda over d, and so on for your locations of the intensities. So we got an example here. You get 550 nanometer light on a single slit, 45 degrees. What is the width of the slit? At what angle is the first minimum produced? So the first minimum is going to be m equals 2. What is the width of the slit? That's the other thing we're solving for. And we've got 550 nanometer light, 45 degree. Sorry, we want we want m equals 1 is the first minimum. We're told that m equals 2 occurs at 45 degrees. And so then you can figure out that m equals 2 with 550 nanometers at sine of 45 degrees. You can get d for the slit width, and then you can plug that back in, and then put m equals 1 to figure out what angle the first one will occur at. Okay, so again, what are you trying to do? You're trying to find the locations of the minima and maximum, and what do they depend on? Slit width, distance to the screen, angle, and yeah, that's, in this case, we don't even care about the distance to the screen necessarily. You will need that if you want to figure out y and l, but if we're just determining the angle, you don't need to know that. Okay, moving on. Okay, the Riley criterion says that the limit of you being able to differentiate two objects, the minimum angle here is this 1.22 times the wavelength of light divided by d, the size of the aperture that you're looking through. So you're trying to take a picture, you're trying to look through something, a telescope, a camera, whatever. When you try to see, or your eyeball, for example, you're trying to see something. So if a car's really far away, it'll look like it has one headlight, and as it gets closer to you, the headlights start to spread apart, and then you can see that the headlights are very far away. So, for example, here, the Hubble Space Telescope, it's got a diameter of 2.45 meters, and assume light hits it at 550 nanometers. If two stars are Andromeda Galaxy 2 million light years away, the question is how close can they be apart and still be resolved from each other. So we want to find this wavelength or this angle between them to figure out the maximum distance that they can be, depending on the wavelength of light. So we've got our 1.22, we've got green light coming in, the diameter of the aperture for Hubble is 2.4 meters, so we get this many radians, and then you imagine your angle is here, we're 2 million light years away, and then how far apart can these two be if that's the angle? and they could be, so the closest stars we could see that far away, we could resolve between each other, gives you 0.56 light years. So that's what that's trying to tell you, is that, you know, when you zoom in on something, there's a limit because of diffraction on how well you can resolve 2 points of light, and it's you know, has very little to do with, excuse me, your camera, other than the optical, the diameter of the lens that the aperture of the thing you're looking at. So there's a fundamental limit to how well you can see or resolve something that's far away. Okay, and we got some examples here for telescope and microscope. Okay, so now we're talking about the wave nature of light. There's a thing called thin film interference, and thin film interference happens because when light goes into one medium, it gets refracted, and then the first ray will be reflected. The second ray will also be reflected back out, but after it's refracted. So there's a little bit of a time delay here, a thickness. And what that means is that when ray 1 reflected off the first surface and ray 2, which also comes towards your eye but is after it goes through the second film, they interfere. And the interference, again, this distance here is the path length difference between this ray and that ray. And that difference leads to a change in the wavelength. So the wavelength of light is going to be different. And their equation for it, I thought they had it up here. Okay, so let's say you've got these lenses, 2 lenses. One is 1.38, the other one's 1.52. What is the thinnest film it can be if the index is 1.38 and you've got 550 nanometer light going on the surface of the glass? And so we've got a glass layer, so we've got glass with this thin coating on it. Okay, and so we're going to have light coming in, reflecting off, another ray of light reflecting off. So this coating thickness is going to determine the extra path length that we are setting. So this, we're assuming the ray is going to come in, I think it says this, incident normally. So that means the light is going to come in, bounce, bounce, and back. So you're going to have a reflection up and the second reflection up here. So the path length difference is literally going to be the thickness, or 2 times the thickness, because we're looking at it at an angle here to exaggerate it. But if the ray of light comes in and then you have one ray reflected and it continues in and reflects again, then these two, you just have path length 1, path length 2, and they add up. And then so all we care about is that the case for destructive interference is when the path length difference 2t, 2 times the thickness. So we need our wavelength to be 2 times the thickness to solve for when the case is that this thing goes out of interference. The wavelength inside the material depends on the index of refraction. So you're going to take your 550 nanometers in, divide by the index of refraction of the coating, and then that's going to give you the N2. And so your case for thickness is that 2t is equal to the wavelength over our index of refraction in there, divided by 2, because we want it to be half of a wavelength out of phase. And then you solve for that, and here's the thickness, 99.6 nanometers. So that's the case for the thinnest possible thickness to kill some reflections. So that's the idea, is that this reflection is canceled out by that reflection, and then you don't see reflections. So that's the main idea with these coatings, is to limit the reflection. Okay, another effect you get is when your ray goes through more or less air, and then you get these things called Newton's rings. and it's this kind of rainbow effect. And again, it's an interference pattern. It's because light is made of waves, and as they pass through different distances, the angle is larger than shown, just FYI, then you get these effects. So again, it's all about path length differences. So you don't have to, we're not really going to do problems like this. They're pretty hard, actually. So we're not going to worry about it, but you should think about what's going on there to get that interference. Okay, finally we have polarization. And turns out that light is a wave. It can be polarized, and it's usually polarized in the direction of the electric field. So if I draw a wave like that, the polarized direction is up and down. If I draw a wave like this and it's traveling that way, then the polarization is left and right. So here's a picture of polarized glasses. Sorry, someone has polarized glasses here and no polarized glasses here. And basically the polarizer, when light hits a surface and is reflected, it's polarized. So you can wear polarized sunglasses, which limit all of those reflected lights because they all reflect to a certain polarization. Okay, so polarization is just the orientation of a light beam. As light travels, it can be oriented any direction 360 degrees around. And the idea here is you've got a polarizer, and when light of the correct polarization enters the polarizer, it passes right through it. If light is polarized in the wrong direction, it's attenuated and you don't see it anymore. So let's say you've got light that's unpolarized. So this is just the electric fields are pointed in every direction. You could have a polarizing filter here, and then what's left afterwards is light that's completely polarized in a vertical direction. So the intensity changes by after light goes through a polarizer. Let's see, it should say here somewhere. Well, let me look for this. Okay, well, when you first go through a polarizer, so for example, this polarizer, when the light goes through it, it only picks this wave. After it goes through, the polarization at any point is equal to the initial intensity of the light, the intensity of the polarized wave. After you have some light going through a polarizer, and the polarizer is at a certain angle with respect to the ray, then the polarized light afterwards, the intensity afterwards, the polarizer is reduced by cosine squared theta. Okay, and so that's the idea here, is that what you're doing is you're taking the reason the cosine comes in here is because you're taking the component of the vector which is along the polarizer axis, and so that's the cosine of the angle. So that's what that gives you. Let's see. Blah blah blah. There should be another example here. Okay, so anyway, so yeah, run through this example. It's really simple idea. That when light passes through a polarizer, depending on the angle of the polarization. So for example, you have unpolarized light, it goes through a polarizer, and then it gets polarized here. If you have a second polarizer here that's perpendicular to the initial one, then it dies. It dies forever. Let's see. Okay, now there's a special thing. When unpolarized light hits water or glass or anything, it is reflected polarized. Okay, and this is why polarized sunglasses work, is because light that's reflected gets a certain polarization. Blah blah blah. Yeah, there's a special angle. And the reason there's a B here is because it's called Brewster's angle, or Brewster's law, or Brewster's angle, which says there's a special angle where when light comes in at that angle, it's fully polarized when it bounces out. Fully polarized. and that angle is just the ratio of the indices of refraction. So if you go from air to water, then you'll put N1 is air, 1, N2 is 1.5, let's say, for glass, and then you solve for what the angle is for that to happen. There's a little bit of an explanation here trying to explain how polarization works in your molecules. And here's an example here. What angle will light traveling be completely polarized when reflected from water? And so then you put your air as 1 and water as 1.333, and you solve for the angle, and at 53.1 degrees, rays of light coming in at water will be completely horizontally polarized. So that's called Brewster's angle. And yeah, the sky, I think this is what this is. The sky is polarized. So if you wear polarized sunglasses and you look around at the sky and change your head and rotate it, you'll see that the colors of the sky change a little bit because you're changing the polarization direction. Okay, LCD screens, there are little polarizers in there that are turning the lights on and off that are pretty cool. Yeah, there's some interesting things there. And that's basically it. Okay, bye.